Unit 1.7, excuse me, lesson 1.7 is brought to you by LEGO Stormtrooper Man. So what we're going to do, just real basic stuff here. We're going to look at the idea of large and small numbers in the context of scientific notation and being able to convert between the two. And we're going to use Newton's law of gravitation to attack this type of situation. So here is Newton's law of universal gravitation, and it is that the force of gravitational attraction between two different masses, m1 and m2, is given by this formula where you have some constant known as the gravitational constant times m1 times m2, so the mass of the two objects divided by the radius squared between the two objects. Now, we could write this formula this way because that g is just multiplied in the numerator, so I'm not quite sure why I have it separate. Okay, so here goes. So the g is a constant. We look carefully at the equation that describes gravitational constant. So let's describe the relationship between the force between objects and the distance separating their centers. That is, if the distance goes up, what happens to the force? Well, if you look closely at the formula, this is where the distance between the two forces shows up. By the way, if you're wondering what happened to my paper here, my cat knocked over my water bottle and I had this on my desk and it got wet. That's what that is. Okay, so if this distance increases, that means we're dividing by a larger number. So what happens when we divide by larger and larger numbers? Well, here's an example. 1/2, then we divide by 1/4, and then 1/8, and then 1/100. Notice what's happening to these values. They're decreasing. So dividing by a larger number decreases the size, decreases the number that the fraction represents. So in summary, what happens when we take things further apart? The force decreases. So the further away two objects are, the less force that they enact on each other. Okay, well, we'll do the same thing. What happens, the gravitational force and the mass of the first object, m. In other words, what happens if we increase m? Well, notice that m is in the numerator, so the force will increase. In fact, if we change either of the two masses and make them larger, the force between the two objects will increase and increase and increase. So the larger the mass, the more force that will result. So why can't you feel the gravitational attraction between you and the Earth, but not between you and the person sitting next to you? Well, that should be clear. The mass of the Earth, we'll say it this way, drowns out the mass of the person next to you. Of course, if we were in a face-to-face class, we wouldn't be able to see a person next to us. In our current situation in Zoom, also the distance between you is quite large. But the point here is that the Earth's mass is so huge that you cannot feel that gravitational pull of that person next to you. Okay. And then here, 4 says, why can you feel it between you and Earth, but not you and Jupiter? The distance between you and Jupiter is so great. Oops, I should capitalize that. We'll just put large, and we should note that the distance between you and Earth is not so large. Okay, so that's just a taste of what's going on with this gravitational force formula. And now we're going to jump into that scientific notation stuff. Here's some crazy numbers. So the force of gravity between the Earth and the Sun is strong enough to keep us in orbit because even though you're about this many meters apart, the mass of the Earth is this. That's a huge number. And the mass of the Sun is this, which is even larger, both in kilograms. So those are kind of annoying to write. I mean, look at what the person had to do to type those out. So scientists and mathematicians came up with a handy way to write really large numbers like this that have tons of zeros. And here's like the first five. 10 to the first power is 10, 10 to the second power is 100, 10 to the third is 1,000, the fourth is 10,000, the fifth is 100,000. Notice that the number of zeros here matches the exponent. And that leads us to scientific notation. I'm going to write the general form. We have some number, we'll call it A, where this is a number between 1 and 10. Actually, it needs to be less than 10. And then we multiply that, and often we use the multiplication button, or the X symbol, times 10 to the n, and n here has to be an integer. Meaning, excuse me, it can be a number like -3, -2, -1, 0, 1, 2, 3, and then continuing on in either direction in that form. So that is our definition of a number in scientific notation.